position for SPH 4C or SPH 3U. You, of course, have this handout in front of you, and I'm going to fill in some of the blanks here and do a little explanation. I expect you to follow along. So the first term you might hear with motion is called position. And position is, where an object is at a point in time, and it's always compared to a reference point or a home position. The symbol we give position is not, this is sort of the mathematical symbol, is a D, and it is V or S means vector or scalar. And we'll talk more about those in a little bit. But for now, V, you might be able to figure out it's a vector. And what I mean is, Ferd is standing 15 meters west of the ice cream stand. Okay, so that's how I refer to position. There's no displacement is how much position has changed. So it's the difference between start and finish positions. And you might remember from math that sometimes we use a little triangle to refer to change in, from slope, rise over run, change in y over change in x. It's delta, and the triangle means delta. It as well as a vector, and hope you start to see that the vector refers to this, okay? So if I use a little example, Ferd moves from his location above, which was 15 meters west, to pick up a nickel that is located 20 meters west. So his displacement is the change, which is 5 meters west. That's the difference between start and finish. No real equation for that either. Distance is actually the distance that is traveled by some object. It has no reference at all. And its symbol is just a D, and it is S for scalar. So in this case, we say, okay, Ferd walks 10 meters north. He turns around and walks 5 meters south. His overall displacement from his start position is 5 meters north because he ended up 5 meters north of where he started. But his distance traveled is the whole thing. It's 15. His distance is 15 meters. And again, there's not really a formula for that. And I'm just going to take this second now to say a vector is a quantity that has direction. And a scalar is a quantity that does not have a direction. And you can tell a vector from a scalar a few different ways. First of all, the first way you can tell is this arrow. So if something is what we call a vector quantity, then it has an arrow over top of the symbol, okay? And the other way is here. When you refer to a vector, you say, 20 meters west. And later on, we'll talk about positive and negatives. It would be plus 20 meters or minus 20 meters. But, excuse me, we're talking about distance in this case. That's a scalar. It's just 15 meters, period. It's not 15 meters east. It's just 15 meters. And that's what distance is, or a scalar is, compared to a vector. If you need to pause, go ahead. Just a few other terms. Velocity. Velocity is a rate of change of position. You might not remember from grade 9, but when you did slope in grade 9, slope was a rate of change. And we give velocity the symbol, I'm going to do a cursive V, that's a lower cursive. And look at that, it's got a vector symbol, so yes, it's a vector, V for vector. And so what I mean is, if I say he travels 200 kilometers east, and it takes him 2 hours, his velocity is 100 kilometers per hour east. So the key thing, I guess, is having that direction in there. And velocity can be found, there is an equation for it. Velocity is displacement, change of position, over time. Okay, so T for time. Sometimes we do delta T, and that means elapsed time. I'm a little bit lazy with that. I always think of it just, T is time, whether you have a delta or not. It's how much time has passed. It's not the time of day, it's how much time has passed. Okay, so speed. Speed, however, is similar to velocity, but it's how fast an object moves. And Ferd walks around the block. He walks 25 meters east, then 20 meters north, then 25 meters west, then 20 meters south. And it takes him an hour. His speed is 90 meters. That's how far he travels per hour, right? Now, his displacement, however, if he walks a full block, 25 meters east, let's see, he drives 25 meters east, 20 meters north, 25 meters west, 20 meters south, right? So his start and finish position are the same, So delta D, his displacement is 0, while his distance is the full 90 meters, right? So his velocity is 0, but his speed, which is symbol V, is 90 meters an hour. Okay, so speed is a scalar, and speed equals this distance over time. And then there's acceleration, and it's the rate of change of velocity. It's how fast something speeds up, slows down, or changes direction. It is A, at least that would make sense, A for acceleration, and it is a vector. Hard to give I'm not going to give a solid example, but you could say, I'll just say it out loud, that, if you speed up from 0 to 90 kilometers per hour in 10 minutes, then his acceleration is how much velocity changed over time. Acceleration equals v2 minus v1 over t. And what that means is 2 means his final velocity. So it's his final velocity minus his starting velocity over time, or change in velocity over time. Okay, so those are the basic terms. Quick little thing I want you to fill in as well is copy down this right here. And I'm not going to have it on the video for very long because you can just pause it and write it yourself. I'll just go through the basics and then you can fill it in yourself, okay? So just a quick thing. First of all, if I say the term kinematics, what I mean study of motion. So I use the term motion and kinematics almost, back and forth, like the same thing. Average and instantaneous velocity. This is important to understand, so especially when we talk about acceleration. If you're looking over a time period, we know that an object may change velocity during that time, but we assume that it's constant. That's if we're talking about average velocity. For example, if you drive 200 kilometers east and it takes you 2 hours, you'd say, whoopsie, I made a typo there. You would say that his average velocity is 100 kilometers per hour, because he did 200 kilometers in 2 hours. However, you pretty much know that over that 200 kilometers, he didn't drive 100 kilometers per hour the whole time. He probably sped up and slowed down, just averaged out to. But this is what we care about, is average. Sometimes, though, we may look at at any point during a trip, you may look at your speedometer and realize you're moving, say, this speed and this velocity, at that angle, north 30 degrees east. That would be our instantaneous at that moment in time. So most often we care about average, but sometimes we care about instantaneous. And when we're dealing with average, the only, and again, you can pause this if I'm going too fast, but the only equation we deal with average velocity is this one that I showed you already, right? But when dealing with instantaneous velocity, there's many relevant formulas. And the most important one is the acceleration formula, which is just, I showed you this already too. And the idea is that, with the acceleration formula, that v2 is the instantaneous velocity at the final time, and v1 is the instantaneous velocity at the initial time, and t is the elapsed time. We'll talk more about acceleration another day. But I did want to get those notes down, and I'll just stop the tape here. Again, if you need to go back and copy anything, you go right ahead. And that's it for today.